everything that we've talked about so far in temperature and thermal energy and heat, we've talked about basically raising the temperature of something from 40 to 80, or the temperature of water is going from 20 degrees Celsius all the way to 90 degrees Celsius. We've never talked about what happens when you take an object or a substance through a phase change, through two different states of matter. And that's what we're going to talk about today. So as a substance is heated or cooled a lot, it will go through all three states of matter, right? Depending on where you start, the temperature that you start at. Okay. So let's think about water, and let's think about basically what we see when we heat water. So we're going to start with a heating curve. Okay. Now this is just arbitrary. This is more of a sketch than it is a graph. So it's a heating curve. Here's a temperature. Pick two arbitrary points, 0 and 100, and here's time. So as time ticks away, what's going to happen as we heat up water? Well, we get this kind of a relationship. Okay, and it's kind of like a zigzaggy line. And what we see is, of course, a couple different things. Of course, this 0 degrees Celsius for water, this is called the melting point. Okay, so when water gets up to this point, it starts to melt. Right through this middle section, of course, the liquid water is heating, and then we get to this point up here, which is the boiling point. Now, something that's interesting about the melting point and the boiling point is that for ice to melt and turn into water, it takes time. And for water to boil and turn into steam or to vapor, right, it takes time. But we'll notice that during this time, the temperature doesn't change at all. It stays exactly at 0 degrees Celsius. Here, the temperature doesn't change at all. It stays exactly at 100 degrees Celsius. And then once it's become a steam, it then continues to heat. Right? Once it becomes a liquid, it continues to heat. So these little plateaus here are very indicative of what happens in all substances when they reach their melting point and their boiling point. Right? We could also show you a cooling curve, and a cooling curve predictably looks the exact opposite to the heating curve, except this up here we of course call the condensation point, right? So it's where the steam condenses into a liquid. Here the liquid cools off during this middle section, and down here we don't call it the melting point, we call it the freezing point. But again, you've got these same plateaus. So these give us a hint about something. Okay, basically we notice that those two parts of the graph that are associated with phase change, the temperature doesn't do anything. And so energy's got to be conserved though. So if we're pumping heat energy into this substance and its temperature's not changing, then something's got to be going on, right? Because think about that equation. Heat energy is equal to mass times specific heat capacity times the change in temperature. Well, for a sample of water, if we're pumping heat energy in, we know that the mass isn't changing, specific heat capacity is a constant, and we know that the temperature is not changing. So there has to be something else that's going on here. And in fact, there is. There's kind of like a hidden energy component. It's almost like a potential energy. It's a stored energy that's associated with any change of state, and we call it latent heat, right? So not specific heat, but latent heat. And it's released when something condenses or something freezes or something melts or something vaporizes, right? So there's two types of latent heat. The latent heat of fusion, and we use the latent heat of fusion for freezing and for melting, and the latent heat of vaporization, and we use that for boiling and condensing. Okay? So we're going to take a look at how we do these things. When you see the equations, they're very, very straightforward, but it's a different type of heat energy. So the latent heat of fusion is the amount of energy that's required to melt 1 kilogram of solid matter. And here it is. The latent heat of fusion, just like the specific heat capacity, just like density, is characteristic of the substance. And the amount of heat energy that's required to melt 1 kilogram of any substance is equal to the latent heat of fusion times mass. Right? The latent heat of vaporization is exactly the same, but instead of using LF for the latent heat of fusion, we use LV, and this is basically what's associated with boiling and condensing. Okay. All right, so let's take a look at a very quick example. A 0.27 kilogram sample of material requires 8.91 times 10 to the 4th joules of energy to melt it without raising its temperature. What is the latent heat of fusion for this material? Well, we've got 0.27 kilograms. We've got 8.91 times 10 to the 4th joules. What's the latent heat of fusion? We can find out by using the very simple ratio of heat energy over the mass, 8.91 times 10 to the 4th divided by 0.27. And we get 3.3 times 10 to the 5 joules per kilogram. So that's the latent heat of fusion. Okay. We can also look at a very similar example, how much heat's required to change 0.20 kilograms of water from liquid to a vapor. And so we're looking at water, we're changing it from liquid to a vapor. So we're going to boil it, but we're going to boil all of it. How much heat does that take? All right, so here's the mass that we've got. Here's the latent heat of vaporization for water. How much energy is that? So we can rearrange, substitute. We have 4.6 times 10 to the 5 joules. So it takes a lot of energy. 4.6 times 10 to the 5, that's 46,000 joules of energy required. That's a heck of a lot, right? That's a lot of energy that we need to boil this much water and to boil all of it. That's a ton of energy. 4.6 times 10 to the 5 joules. All right. Last example for now, and we're gonna go on to something a little bit different. What would be the total amount of heat energy that would be required to warm a solid sample of water? So we've got ice. We're going to raise it from minus 30. We're going to melt it, and then we're going to heat it up all the way to 80 degrees Celsius. So this is a big task. So first of all, we have to think about what we're going to do here. So we have tons of constants. We've got the specific heat capacity for water, the specific heat capacity for ice, the latent heat of fusion for water. We've got initial temperatures, we've got midpoint temperatures, we've got final temperatures. Holy cow, we need a strategy to kind of solve this problem. So this is how we're going to lay these problems out. We're looking to find some total amount of heat energy. Well, the first part of energy is going to come from warming it up, because we have to take it from minus 30 to 0, right? Because it's going to melt at 0, but we can't go from minus 30 all the way up to 80. We have to go first from minus 30 to 0. Okay, fine. So let's do that. Then it's going to melt, and we know that there's going to be some energy that's got to melt it. Then finally, we've got to take it from 0 all the way up to 80. Now, why do we have to do these two things separately? Well, because this down here, we're warming ice, and ice has one specific heat capacity, which is actually quite different than water's specific heat capacity, where we're warming here. So we have to do a section for here, melting, and then a section for here. So let's put everything together. We've got the mass times the specific heat capacity of ice times T2 minus T1 plus the latent heat of fusion times the mass plus mass times specific heat capacity. And here I've used T3 minus T2 because this is kind of like the third temperature in a row. We can substitute all of our values and simplify each of these terms to arrive at 72,900 joules. So 7.3 times 10 to the 4th joules. That's a lot of energy. And you'll notice that we took a very, very strategic approach, right? We looked at this first little bit of warming, then this fusion, then the second little bit of warming. So basically, this process requires 7.3 times 10 to the 4 joules of energy, and that's where we're at. So this is another type of problem when we're talking about finding that total amount of heat energy that's required. Okay, now a little bit of a departure from this. We're going to talk about calorimetry, which is the lab that you're going to be doing in the next few days. Okay, so a calorimeter is a device that's used to measure heat transfer. Okay, so a calorimeter is basically an insulated vessel that's going to keep heat energy from being lost to the environment. So very often it's kind of like an insulated cylinder with a lid, a thermometer, and then a rubber stopper so that we can add some stuff in here. Okay, a diagram of a simple calorimeter is shown right here. So in general, a calorimeter allows you to control all aspects of heat transfer, right? And use the unknowns to find basically the test substance specific heat capacity. And that's what we're going to be doing. I'm going to give you a metal sample. You're not going to necessarily know what that sample is made of. And you're going to have to measure very carefully so that you find the specific heat capacity of your metal and then determine what type of metal it is. Okay? And so this right here, this example number 4, this presents a pre-lab question for this laboratory that we're going to do tomorrow. Okay, so a 0.7 kilogram piece of aluminum is heated to 100 degrees Celsius in boiling water. And that's exactly what we're going to do in this lab. It's quickly placed into a calorimeter that contains 0.2 kilograms of water at 20 degrees Celsius. The final temperature of the calorimeter was determined to be 54.4 degrees Celsius. What is the specific heat capacity for aluminum? And so what we do is that we've got the mass of aluminum, the mass of the water, the initial temperature of the aluminum, the initial temperature of the water. We want to know what the specific heat capacity is. We know what the specific heat capacity of water is, and we know the final temperature. And we can put these together exactly the same way as we did these heat exchange problems, and you'll see that this is very similar to the questions that we were learning in lesson number 7, where we've got one thing that's gaining heat energy, one thing that's losing heat energy. We can make our substitutions, and we can isolate the specific heat capacity of aluminum, and when we get down to it, we find the specific heat capacity is 905.3 joules per kilogram degree Celsius. So this is just something to think about as we come up to our lab in the next couple of days. This is exactly what we're going to be doing. And then we're going to be trying to identify the metal that we have given the specific capacity.